but I don't want to put it in the form of an exam, because then there are always going to be people who find the actual exam more difficult than the mock exam, and they're going to complain and stuff like that. And also, if I'm trying to make a mock exam, it's just a lot more work, because you have to get the length right and to get the type of the exercises right. So if I find the time, I can just make a problem sheet 12, which has exercises from every chapter, from every section of the course, and then you'll have some more exercises to practice that I could do. But I'm not sure when I'm going to do it. If I find time next week, I might do it before Christmas. Otherwise, it'll be next year. Also, the ones who handed in problem sheets, I haven't managed to mark them yet. So you'll have to come and collect them next year, because I'm away from next Monday till maybe 7th of January. So, yeah. Okay, so I think it's time to start. So today, so essentially last time we finished the material of the course. So today we have time to look at some examples and to discuss some more exercises from the problem sheets. And there's one more remark that I skipped earlier in the lecture and that I wanted to give you. But apart from that, today it's going to be examples and exercises. There's one exercise from sheet 10, which I want to discuss first. And then after that, I'll give you this remark that I skipped earlier in the lecture, and then we can look at an example for Fubini's theorem. But this exercise is kind of important because it's one where you actually compute the product measure of a set in a product space using the definition of a product measure. So we're doing exercise 1 of part B, sheet 10. So we have two measure spaces, x, sigma x, and mu, which is two specific measure spaces. The first one being the real numbers with just the power set and the Dirac measure at 0. And the second one being the real numbers, the Lebesgue measurable sets, and the Lebesgue measure. And then the task was to compute the following two things. First, n times delta naught of the following set, x, comma y in R2, such that x squared plus y squared is equal to 1. So this is just a circle with radius 1, right? And the second part of the exercise was to compute m times delta naught of x, y in R2 such that x squared plus y squared is less than or equal to 1. So this would be the disk. So the part A is to compute this product measure of this circle, and part B is to compute the product measure of the entire disk. And this you can do just using the definition of the product measure without any complicated theorems. So to solve this, let's look at part A first. Okay, so if we want to compute the product measure of this set, then we have to take the definition of the product measure. So that's definition 7.7, which says that mu times nu of a set S is the integral over x nu of the slice Sx d mu of x, or equivalently you can take the integral over y mu of the slice Sy d nu of y. So if we want to compute m times delta naught of the set, we can either choose this formula or this formula, whichever we please, whichever we feel more comfortable with. So that's what we're going to do. And in my solution, I chose to use this, where I take the slice Sy. So if we want to apply this formula, first we have to determine what these slices look like. So by definition, so let's call this this circle, let's call this S. So S is just this set xy such that x squared plus y squared is 1. Then for a fixed point y in R, the slice Sy was defined as all x in R such that x comma y is in S. Okay, so if you look at the definition of S, this is just all x in R such that x squared plus y squared is 1. Yeah. Okay. So if we look at this picture of the circle, then this slice is the following. Okay, so say the point y is somewhere here on the vertical axis. Then how do you get this slice? You take all x such that x comma y is in S, which means you draw a horizontal line through y. Okay, and then where this horizontal line intersects the set S, these are the x values that lie in the slice Sy. So you take these 2 points that lie on the circle, on the intersection of the circle and the horizontal line. Then you go down, take the x value, and then the union of these 2 points is the slice Sy. Okay. So generically, Sy for the circle line looks like this. If y is somewhere between 1 and -1, then you always get 2 points, somewhere between 1 and -1 on the horizontal axis. If y is outside this interval 1 - 1, then this slice is just empty. There are no x, such that this is true. And then if y happens to be exactly 1 or exactly minus 1, then this slice as y is precisely 1 point, which is x equals 0, right? If you move this point y and this horizontal line, if you move this up, then these 2 points will move together, move towards each other, and if y is exactly plus 1, then x has to be 0, so that this is satisfied, right? So that's what this slice as y looks like. And well, this is what it looks like in formulas. And in fact, if you want, you can even simplify this set. You can write this as plus minus square root 1 minus y squared, right? If you just solve this equation for x. So it's this when y is between 1 and minus 1, and otherwise, if y is outside this interval, it's just empty, okay? So this is the slice as y. And now we can take this and plug it into this formula. So what I'm going to do is I'm going to apply delta naught to this slice as y. So in this definition of the product measure, mu is delta naught and nu is the Lebesgue measure. So if you want to compute this integral, we have to compute delta naught of sy. Well, and what is this? This is, by definition of the Dirac measure, it's 1 if 0 is in sy and 0 otherwise. So we have to determine when 0 is in sy to determine when this function is 1 or 0. But I've already said this, right, when I explained this picture. 0 is in sy if and only if y is either 1, plus 1, or minus 1. Because then these 2 points on the horizontal axis merge and meet at 0. So if y is plus 1, then sy just contains 0, and if y is minus 1, then sy also just contains 0. So we have 0 is in sy if and only if y is equal to plus minus 1. So now we've determined this function completely, right? This function, as a function of y, is 1 if y is equal to plus minus 1, and 0 otherwise. So this this function delta naught of sy looks like this. 1 minus 1, it's 0 everywhere except at 1 and minus 1, and at these points it's 1. Okay? That's what this function looks like. And now, by definition of the product measure, we have to take this function and integrate it with respect to the Lebesgue measure in y. So we have so in other words, delta naught of sy is just the characteristic function of the set 1 minus 1, right? So m times delta naught of s is equal to integral over r this function with respect to the Lebesgue measure. And now we can just plug in this characteristic function. So this is integral r chi 1 comma minus 1 of y dm of y. And what is this integral?
0?
Yes, 0. Why is it 0?
Because it's a simple function, so you just pick the measure of the set minus 1, 1, and that's countable. So it's a 0 measure?
Yes, exactly. So in other words, this function is 0 almost everywhere with respect to the Lebesgue measure. So yeah, that's just 0. Okay, so we solved part A, right? We've computed m times delta naught of this circle S. So, and in part B we'll have the entire disk, and we have to compute a similar measure of this entire disk. But before we continue, are there any questions about this, about part A? If that's not the case, maybe I'll leave the exercise there. Okay, and I'll continue here with part B. Okay, so in part B, the beginning is pretty much the same. Let's choose a name for this set, for this disk. So let's call it S tilde. So now S tilde is the full disk. And now again, as before, the first thing we have to do is to determine what these slices are. So let me draw this again. Okay, so S tilde is the full disk. So if we do the same thing, so if we want to determine the slice, let me just write down the formulas first. S tilde y, the slice is by definition of x in R, such that x comma y is in S tilde, which is the same as x in R, such that x squared plus y squared is less than or equal to 1. Right? So now if we pick a point y on the vertical axis, we do the same thing as before. We draw a horizontal line through the point y, and then we have to take all the points, all the x coordinates of points where this horizontal line intersects the set S tilde. So the intersection of y and S tilde is everything between these 2 points now, right? Everything between these 2 points belongs to the intersection of S tilde and this horizontal line, and then so if we go down and take the x coordinates, we get this interval. So this entire interval in this case would be the slice S tilde y. similarly to before, if we raise the value of y, so if we shift this upwards, then the length of this interval decreases, and as y hits the point +1, it shrinks to a single point, and if y is above +1, then this section is just the empty set. So now, as before, the next step is to determine delta naught of S tilde y. So so this is, by definition of the Dirac measure, 1 if 0 is in the slice and 0 otherwise. So in this case, so 0 has to be in this red interval. Then this function is 1, and otherwise it's 0. So when is this the case? Well, here 0 is in the interval, right? If we move y up and down, 0 will always be in the interval until y leaves this interval from -1 to 1. So this function, delta naught of Sy, will be 1 whenever y is between 1 and -1 and 0 otherwise. So in this case, this function is the characteristic function of the interval from -1 to 1. Okay? And now again, by definition of this product measure, we have to take this function and integrate it over R with respect to the Lebesgue measure. So this is the general formula, and then we can replace this delta naught of S tilde y by this characteristic function. And now this is easy to compute again, right? This is just the integral from -1 to 1 over a constant function, which is constant 1 on that interval. So this is just equal to 2 in this case. So, and that's the solution of part B. So for the circle line, we got 0. For the full disk, we get 2. So are there any questions about part B? Okay, so if not, then let's finish the final bits of the lecture. So as I said, I wanted to give you one remark that I skipped in section 4. That was remark 4.46. So this is in the typed notes. You can find this remark. And the remark says if you have a measure space X sigma mu, and you have a subset of X which is measurable, then this subset E can again be considered as a measure space in its own right. We've never talked about that, and I think it's important just to know this. So subspace of measure spaces are again measure spaces with the following definition. So then E can be regarded as a measure space in its own right if we define the sigma algebra and the measure in the following way. So sigma, this sim is sigma restricted to E, by definition is the following: A subset E such that A is in sigma. So as the new sigma algebra, we can just take all the measurable sets which happen to be subsets of E, and then that's a sigma algebra over E. And then as a measure on this new measurable space E comma sigma E, you can just take mu restricted to E, which by definition means you just take the measure mu and restrict it to this sigma algebra sigma E. So really, you just do the most naive thing you could do. You take all measurable sets which are subsets of E, and then you just restrict the measure to that sigma algebra, and then you get a new measure space E comma sigma E comma mu E, and that's a measure space again. So so in this way, subsets of measure spaces can be regarded as measure spaces again. Examples for this: for example, you could take sigma to be the Borel sigma algebra on Rn, or to be the Lebesgue measurable sets, on Rn. And the measure could be the Lebesgue measure, and E could be some bounded measurable set in Rn, or it could be any measurable set, right? For example, a ball or a rectangle. And then in this case, when the sigma algebra is the Lebesgue measurable sets, usually you don't change notation. Usually you don't write this, but you just write sigma L again. So when it's clear from the context which subset we're considering, then people just write sigma L, and they don't always write sigma L restricted to E. And the same for the Lebesgue measure. And now this is kind of useful because now things like we can write down things like interval from 0 to 1 with the Lebesgue measurable sets and with the Lebesgue measure. Now things like this make sense. We can write down things like this, and then this is a measure space. We don't have to take Rn here. We can take any subset. Or for example, we can write down things like L1 of 0.1 times 0 infinity with Lebesgue measurable sets and the Lebesgue measure. Now things like this make sense. So whenever we write subsets of a measure space, this is automatically a measure space by just this definition. And then, for example, here, if you take the interval from 0 to 1, integrals with respect to this measure are exactly the same as integrals with respect to the Lebesgue measure on the whole space if you integrate from 0 to 1. So nothing changes. You can. It's just sometimes it's convenient to write subsets as measure spaces in their own right. So now I think like this makes sense. So yeah, this appears quite often in the literature, in textbooks, when whenever integrals go from 0 to 1, then people write things like this, for example, and they mean all functions which are integrable on this domain. So that's why it's kind of important to know about this this remark. So I just wanted to add this. And yeah, we have some time left. So okay, so this is really all I wanted to say in terms of the lecture. And now we have time to discuss examples and other exercises. So we'll just do examples and exercises until we run out of time, basically. And in the lecture notes, there's one example for an application of Fubini's theorem, which I want to show you now. Because so far, okay, we've seen the theorem, and we've seen one example where both Fubini and Tonelli don't really tell us anything, right? We had this function where we were not allowed to swap integrations. And now, of course, it would be nice to see an example where you can swap integration and to see how you actually use these theorems. And that's what this example does. And it actually shows how it can be useful to prove things which initially don't look like you would need Fubini's theorem. So it turned out if you do the example properly, step by step, it's quite long. So we'll just start the example and then maybe have a 10-minute break and then continue. So the problem is, so the example application of Fubini's theorem is the following. So show that limit n to infinity, r to infinity, sorry, capital R, it's a real number, integral from 0 to r sine x over x dx is equal to pi over 2. Okay, and this integral dx, of course, we mean the Lebesgue integral, the Lebesgue measure in this case. So I'm just going to write dx everywhere instead of dm of x because it's shorter. So this can in fact be proved by Fubini's theorem, even though there are no two integrals here that you can swap. But you can introduce a second integral and then swap the integrals, and then you can compute things, and you can take the limit, and then you get this formula. So this is quite neat, but it turns out to be a bit long. So the solution goes like this. Define a function f from R2 to R. So this f is defined on a product space by f of t comma x equal to e to the minus xt times sine x. And then it turns out that this function is actually useful for this problem because the integral from 0 to infinity of e to the minus xt with respect to t is equal to 1 over x. So if we take this function f and we integrate it in t, then the sine x is independent of t, right? So we just get, if you take f and you integrate it in t, then this becomes 1 over x. So the integral of f with respect to t is just sine x divided by x, which is the thing we want to prove something about. So so that's why this function is useful. So this function, a double integral of this function corresponds to a single integral of this function. And if we introduce this double integral, then we can try and swap integrals. So so for any positive r, we have that integral from 0 to r sine x divided by x dx is equal to integral from 0 to r. Now I'm writing this 1 over x as this integral over the exponential function, integral 0 to infinity e to the minus x t dt times sine x dx. So now we have this double integral, and now we're going to use Fubini to swap the order of integration and to first integrate in x and then integrating t. So this equation, let me call this star. Okay, let me just write down what I just said. We want to apply Fubini to swap integrals. So now, and in a way, this is the crux of the problem, right? This is where you have to understand how Fubini works. So, so what do we have to show in order to apply Fubini? Question to you.
I'm sure that f is in L1.
That's right. So remember, in Fubini, one of the assumptions, the key assumption I would say, was that the function has to be in L1 of the product space. So in L1 with respect to the product sigma algebra. Okay, let's write this down. Show that f is in L1 of 0 infinity times 0 r with the Lebesgue measure times the Lebesgue measure and so on. Yeah, let me write this explicitly. So the sigma algebra would be sigma L times sigma L, and the measure would be Lebesgue measure times Lebesgue measure. Okay, so to apply Fubini, we have to show this. How do we show this, that f is in L1 of the product space?
Integrate the absolute value.
Yes, and which theorem are we using there?
Tonelli?
Yes. So, okay. Can you say more words about this? So integrate the absolute value over which space and so on.
But with the same space, and it should be finite.
Yes, that's right. And then how are we using Tonelli?
Because absolute value is non-negative, so we can swap the order to calculate it.
Yeah, it's basically correct. So, so you're right. One way to show that f is in L1 of this product space is to take the absolute value and then show that the integral with respect to m times m is finite. And then by Tonelli, we can write the integral with respect to m times m as an iterated integral. So we only have to show that the iterated integral is finite. And that's how we're using Tonelli. So we're using Tonelli to replace this integral m times m by the iterated integral, first in t and then in x, say. Apply Tonelli to absolute value of f. Okay, and now we have to do some estimates. So we have to show that the iterated integral of mod f is finite. So we know that the absolute value of sine x is bounded by x. for positive x. Right, just because sine x looks like this and x looks like this, approximately. So sine x is below x. I think you can prove this with if you write down the Taylor series of sine x, for example. So we have this upper bound for sine x, which appears in f. So this implies that the absolute value of f is bounded by x times e to the minus tx. Just replace the sine by x. So if we write down the iterated integral, integral 0 to r, integral 0 to infinity, x e to the minus tx dt dx. So this x in the inner integral, in the t integral, we can just move this x in front of the interval because it doesn't depend on t. Then we just have the integral e to the minus tx dt, but that's 1 over x, right? So we can replace this t integral by 1 over x. So this is the same as 0 to r, this x times 1 over x dx. So the integrand is just 1, so this integral is just r. And of course that's finite. And because this is an upper bound for mod f, the iterated integral of absolute value of f is finite. And now Tonelli tells us that because the iterated integral of f of mod f is finite, because of that also the integral with respect to m times m is finite, and therefore f is in L1 of this space. So I'll just write this down here, and then maybe it's a good okay, I'll write it down over here. Maybe then it's a good time to take the break. So this implies that integral, let's write this explicitly. So integral over this space, 0 infinity times 0 r, so this product integral is finite by Tonelli, and then f, well, that's equivalent to f being in L1 of this product space. I'm only going to write the base space now, so 0 infinity times 0 and now we know that f is in L1, so now we can apply Fubini. And Fubini tells us that in this double integral, we may swap the integrals. Okay. Are there any questions up to this point about the example? Yes?
Yeah. In order to apply Fubini, do we not need that it's measurable?
Yes, we do. So, but I mean, it's, well, first I'm sure you can show that continuous functions are measurable, but also on you can show that functions of the type, oh no, that doesn't even work here. So I think one argument that works is that Borel sigma algebra times Borel sigma algebra is a subset of this sigma algebra.
Okay, yeah.
And continuous functions are Borel measurable.
Okay.
And therefore any continuous function should also be measurable with respect to this. I think something like this might work.
Do we have continuity problems at x equals 0? I mean, I know the limit is 1, because x goes to 0.
You mean for this function?
Yeah.
Yeah, I mean, yes, because the limit is 1, we don't have problems. So I mean, you put it equal to 1 and 0, if you like.
Yeah.
But because 0 is a null set, with respect to the Lebesgue measure, it doesn't really make a difference which value it has at 0. So you can just define it to be 1 and then it's continuous.
With questions like this in general, the sort of measurability of it is something that is fair to ignore, or if it's like a continuous.
Not really. I just in this example, if we prove measurability first, it's going to become even longer.
Okay.
And
but if we were to do a question like this, you would expect.
Yeah, we would expect you to show measurability,
Okay.
but here that just wasn't the point. I just wanted to show how to apply Fubini's theorem and how to get from, first you take the absolute value, then you do Tonelli, and then you can do Fubini. But yeah, we should have, I mean, the section on product spaces was fairly short. Maybe we should have had some kind of theorem that says continuous functions are measurable on product spaces. But because, I mean, on problem sheet 10, I think, you showed that the product of two Borel sigma algebras in Rm and Rn is the same as the Borel sigma algebra on Rm plus n. And we know that continuous functions are measurable with respect to this, and then because this is the same as this, continuous functions are also measurable with respect to this, and then because this is a subset of this, I think continuous functions should be measurable with respect to this. I think this is one argument that would work, so this would be my answer. Yeah, but otherwise, yes, you could, yeah, otherwise you'd have to try and use the definition of measurability and look at these pretty images of half-lines and so on. Okay, I hope that answered your question. Are there any more questions?
For like such a long time.
Yeah.
It's what game Return of the Day, like everything on the speed of chase. The green screening is dreadful. It's like prequel.
Oh god, yeah.
But you know, it's what they have at the time.
I'm pretty sure. I couldn't tell you
What?
That's all.
Yeah. Wouldn't like a drop kick one. just look to the side, he does every single thing you want to be beating up a score and punch it in, so nah, you get wrecked, so.
Okay, let's continue. So again, about this measurability, I think you can even take Borel times Borel in this case if you want. I mean, the main difference between sigma L and Borel is that sigma L contains more measurable sets, and therefore you have more measurable functions if you take this instead of Borel. But if you have a continuous function and you just want to integrate it, you could also take Borel, because the value of the integral will be the same, because the Lebesgue measure just does the same thing. So maybe it would have been easier to just take Borel times Borel, and then it would be measurability would be easier to see. But anyway, so we that's where we left off. So we showed that f is in L1 of this product space by, again, first taking absolute value of f, then applying Tonelli, and then showed that the integral of the absolute value is finite. And then, because we knew that f was in L1 of this product space, we could apply Fubini. And now we're allowed to swap integrals in this equation. So we can integrate first from 0 to r in x, and then from 0 to infinity in t. So now I'm just writing the left-hand side of this equation star again. Sine x divided by x dx. Now we know that this is the same as integral 0 to infinity, integral 0 to r. Sine x e to the minus xt dx dt. Okay, and now we can compute this inner integral first, and then compute the outer integral, and this turns out to be easier than well, computing this integral. So in this inner integral, you have to compute this. It's kind of annoying. You have to do integration by parts twice to compute this integral, but there's no way around it. So I think so. The inner integral from 0 to r, sine x e to the minus tx dx. So one integration by parts gives minus cosine x times e to the minus tx evaluated at 0 and r, minus integral from 0 to r cosine x times the derivative of the exponential, so t e to the minus tx dx. And so this is one integration by parts, and now we have to do another integration by parts. And then this cosine term will become a sine again, and then this integral will just become the same as this integral again, and then we can solve the equation, and then we get the integral. So another integration by parts on the right hand side gives the following. So the first term, I'll just leave this unchanged, minus cosine x e to the minus tx evaluated at 0 and r, and then minus, and now partial integration by parts in this integral gives sine x t e to the minus tx evaluated at 0 and r minus integral from 0 to r sine x, and now we have a t squared because we take another derivative of the exponential function times e to the minus tx dx, and this is it. So now if you look at this last integral, this t we can take out of the integral, and then we have integral sine x times e to the minus tx, which is exactly the same as this integral on the left hand side. So we can take this integral, oh, this is a t squared, by the way, sorry. This t should be a t squared because we take another derivative of the exponential function. So now we can take this and move it to the left hand side, and then on the left hand side we have 1 plus t squared times this integral and now this is equal to this and this in these terms in square brackets.
Would it not be 1 minus t squared?
It should be 1 plus t squared, but why? Oh, I think there should be a minus here because the derivative of the exponential function gives you a minus t.
Yeah.
I think that's where I lost the minus sign. But this is what you should get. This 1 plus t squared. So on the right hand side we have the stuff in square brackets, and now I'll just write out these evaluations at r n at 0. So this first one gives minus cosine of x of r, sorry, times e to the minus t r, and then plus, now this evaluated at x equals 0 just gives 1, right? Cosine of 0 is 1, e to the minus t times 0 is 1. So this just gives us 1, and then we have this term with the sign left, and this gives us minus sine r times t times e to the minus tr, and then this sine term evaluated at 0 will just give 0 because sine 0 is 0. So we get nothing. Okay, and now let me rewrite this equation, because there are a lot of terms and it's kind of a mess. But what we really have is integral sine x e to the minus tx dx is equal to 1 divided by 1 plus t squared, right? That's from this constant 1. And then plus other stuff, and all the other stuff will go to 0 as we take r to infinity. That's the important thing. So this is minus cosine of r divided by 1 plus t squared times e to the minus tr, and then minus sine r times t times 1 plus divided by 1 plus t squared times e to the minus t. Okay, so this is the inner integral. This is this x integral on the right hand side. And now we have to integrate this with respect to t and send r to infinity. So if we do this, we get, okay, I'll just copy this double integral that we started with, integral 0 infinity, integral 0 r. No, I'll copy the left hand side because that's what we want in the end. So integral 0 to r sine x divided by x dx is equal to. Okay. So now we have to take the t integral of these three terms on the right hand side. So first we have integral 0 to infinity 1 divided by 1 plus t squared dt, and then minus the other two integrals. Integral 0 to infinity cosine r divided by 1 plus t squared e to the minus tr dt, and then the sine term. Now what I want to show is that if we take r to infinity, then this integral goes to 0, and this integral goes to 0. And this first integral is independent of r, right? So this will just stay there. And treating these two integrals, that's why this whole exercise is kind of tedious. They've been annoying us from the beginning since we did the integration by parts. So yeah, now it's not too difficult anymore, because if you look at this integral, this cosine is bounded by 1 in absolute value, and then this prefactor 1 over 1 plus t squared, that's also bounded by 1, right? So this whole function that we're integrating is bounded by e to the minus tr, just because this prefactor is bounded by 1. So this integral is bounded by the integral of e to the minus tr, this whole integral in absolute value is bounded by integral 0 to infinity e to the minus tr dt. But this integral we had at the beginning, right? We had e to the minus tx. So we know what this integral is. It's just 1 over r. So this whole annoying integral is bounded by 1 over r. And 1 over r goes to 0 as r goes to infinity. So this term goes to 0 as r goes to infinity. And for the other integral, it's basically the same. The sign is bounded by 1. And then we have, instead of 1 divided by 1 plus t squared, we have t divided by 1 plus t squared. But it's easy to see that t divided by 1 plus t squared is also bounded by 1. So this second integral is bounded by the same thing and goes to 0 as r goes to infinity. So now we really get that the limit r to infinity of this left-hand side is just equal to this integral. And then this integral can be computed if you know what the primitive of this function is. And well, it turns out that the primitive of this function is the arc tangent. So this is just arc tangent of infinity minus arc tangent of 0, and at infinity the arc tangent approaches pi over 2. So that's just pi over 2. So in the lecture notes this example is much shorter, but they just, yeah, in the lecture notes it's just a couple of lines and it says how you apply Fubini and so on, but they don't say how you take this limit of r to infinity. And I just wanted to do the exercise completely. And I think this is one way how you can do it. But yeah, the useful bit was, okay, you can introduce the second integral, then you can swap integrations, and then in the end, when the dust has settled, you end up with this integral, which you can just compute if you know what the primitive of 1 over 1 plus t squared is. Okay, so this was an example for Fubini's theorem. And okay, so are there any more questions about this this example? Okay, if not, so I prepared one more exercise from the problem sheets that I could show you if you're interested, because we still have time, and because so this is from problem sheet number 9. And on problem sheet number 9, we didn't really have much time to discuss exercises from there. And I think I only discussed part A in the lecture. And on sheet 9, there was this exercise where you use the uniqueness lemma. And so far, I think we've never discussed any exercises about the uniqueness lemma on the blackboard. So I thought maybe it would be good for us to just repeat, for everyone to see this exercise, how can use the uniqueness lemma in practice. So this is problem sheet number 9, part B, exercise 4. And the exercise was to show that the Lebesgue measure is the only translation invariant measure mu on the Borel sigma algebra of R such that mu of the interval from 0 to 1 is equal to 1. So in other words, if you have some measure mu on the Borel sigma algebra, and you know that on the unit interval it's equal to 1, and you know that it's translation invariant, then it has to be the Lebesgue measure. There's no other way. There's no other possibility. That's quite a strong statement, right? So if you want to, if you want this, which is fairly reasonable, right? The interval of length 1 should have measure 1. So if you want this and translation invariance, then it has to be the Lebesgue measure. So this construction that we did when we constructed the Lebesgue measure, we didn't have any other choice. So the proof of this, of course, uses the uniqueness lemma. So the uniqueness lemma tells us when two measures are equal, and in particular it reduces the question of whether two measures are equal to the question whether they're equal on a pi system that generates the sigma algebra. So, so the solution goes like this. We start with some measure mu. Okay, so let mu be a translation invariant measure which satisfies this. Let mu be a translation invariant measure on Borel sigma algebra of R such that mu of interval from 0 to 1 is equal to 1. And now we have to show that mu is equal to the Lebesgue measure. And we do this the following way. We can consider the following set of intervals. We call this calligraphic A, and it's defined as A, B, so intervals from A to B, such that A is less than B, and A, B are rational numbers. Then A is a pi system, right? If you take an interval with rational endpoints, and you take another interval with rational endpoints, and you take the intersection, then you will again obtain an interval with rational endpoints. So by definition, this A is a pi system. And in addition, the sigma algebra generated by A is the Borel sigma algebra of R. We've seen this a couple of times. Intervals with rational endpoints generate the Borel sigma algebra of R. And now we want to apply the uniqueness lemma. So the aim is to show that mu and the Lebesgue measure agree on this pi system A. Because if mu and the Lebesgue measure agree on this pi system A, then the sigma finite version of the uniqueness lemma so in the lecture notes this was remark 6.6 implies that mu has to be equal to m, the Lebesgue measure, on the whole Borel sigma algebra of R. Okay, and now all the rest of the proof will be to show that this equality is true, so that mu of an interval AB with rational endpoints is equal to the Lebesgue measure of an interval with rational endpoints. And it all starts from here, from this unit interval, because that's the only thing we have. So the first thing we're going to show is that mu of a single point x has to be 0. And this one can do the following in the following way. If we look at the interval from 0 to 1 over n for some natural number n, then this is equal to the following. I'll explain in a moment why this is true. So mu of the interval from 0 to 1 over n is equal to 1 over n times the sum of intervals from k over n to k plus 1 over n. So this sum has n terms, and by translation invariance, mu applied to all of these intervals gives the same value, because mu is translation invariant, right? These intervals all have the same length. They have the length 1 over n. So they're just translates of the same interval, this one. So if I have n terms, then I get n times the same value, and I divide by 1 over n. And then this has to be equal to this measure of the interval from 0 to 1 over n. So this is by translation invariance. And just to draw a picture, what we're doing is we're taking the interval from 0 to 1, and we're splitting it into intervals of size 1 over n, of length 1 over n. So this first point here is 1 over n, the second point is 2 over n, and so on. And now this sum on the right hand side is just the sum over all these intervals up to 1. So these are n intervals, and mu gives the same value for each interval, and because they're just translates of the first interval, all of these have to be the same as mu of this first interval. Okay. Now, so this is by translation invariance, and now we can simplify this. This is 1 over n times mu of the interval from 0 to 1 minus the union of from k equals 1 to n minus 1 of these single points k over n. So this is just because mu is a measure and therefore it's additive. So this is by additivity. Right, so instead of, because all of these intervals are disjoint, instead of summing, I can take the union of these intervals, and the union of these intervals is the same as the entire interval minus the endpoints. So that's just this. So the second equality is by additivity, and then this by monotonicity of measures, this is less than or equal to 1 over n times mu of the interval from 0 to 1. Right? Because this is interval from 0 to 1 minus something, so if we leave out the minus something, we can only make it larger. So this is by monotonicity of measures. And now by assumption, this mu of interval 0, 1 is 1, right? So this is just 1 over n. Okay, so just by using translation invariance and the fact that mu is a measure, we obtained that mu of the interval from 0 to 1 over n has to be bounded by 1 over n. So this is certainly progress. And now that we have this inequality, we can use translation invariance again and get that mu of the interval from minus 1 over 2n to 1 over 2n is bounded by 1 over n as well, right? So we just take this first interval and shift it to the left by half its length. And by translation invariance, that has to be the same as this. So mu of this interval is bounded by 1 over n. But then these intervals, they all contain 0. So this way we can get a statement about mu of the point 0. Because mu of 0 is just mu of the intersection n equals 1 to infinity minus 1 over 2n, comma 1 over 2n, which is the same as the limit n to infinity mu of minus 1 over 2n, comma 1 over 2n, which is limit n to infinity of 1 over n, is bounded by this, which is 0. Okay, so we get that mu of the point 0 is 0. And now again by translation invariance, mu of every single point has to be 0. Okay, are there any questions so far? Okay, so this was step 1 in a way. We used translation invariance and all the other assumptions to show that mu of a single point is always 0. And now we go back to this equation here. So we showed earlier that mu of the interval 0 to 1 over n is 1 over n times mu of this interval 0, 1 minus finitely many single points. Right? And now we know that each of these single points has measure 0. So mu of the interval 0, 1 minus these single points is equal to mu of the interval from 0 to 1. It's not just bounded by it, but it's in fact equal because we don't lose anything by removing these single points. So mu of interval 0, 1 minus these single points, k equals 1 to n minus 1, k over n is equal to mu of 0, 1 minus mu of this union because mu is a measure, and then the second term is 0. So this is equal to mu of 0, 1, but mu of 0, 1 by assumption was equal to 1. So this shows that in this step, where we got this inequality, in fact we have equality. Right? So now we know that mu of 0 to 1 over n is equal to 1 over n, not just less than or equal. Okay, and now again by translation invariance, we know that mu of any translation of this interval, so for example mu of the interval from k over n to k plus 1 over n is also equal to 1 over n. And now we're basically done. Now it's more or less a simple calculation to show that if you don't have k over n and k plus 1 over n, but any rational endpoints of intervals, then still you just get the length of the interval if you apply mu. So I'm not going to do this on a blackboard because it would be long, but what you get is that mu of p divided by q, comma r divided by s, so two rational numbers as endpoints, is r divided by s minus p divided by q for r over s and p over q rational numbers. And of course r over s should be larger than p over q, and so on. So this follows by calculation from this last statement. But then, right, this is just the length of this interval, and the length of the interval is exactly the Lebesgue measure of this interval. And this completes the proof, because we've shown that for any interval with rational endpoints, mu and the Lebesgue measure agree. And this pi system that we started with was precisely defined as intervals with rational endpoints. Okay, so we know that mu and m agree on A. And now the uniqueness lemma tells us that mu and m agree on the sigma algebra generated by A. But as we noted at the beginning, the sigma algebra generated by A is just the Borel sigma algebra. So mu and m agree on the Borel sigma algebra. Okay, this took slightly longer than I wanted. Okay, so we're out of time now. I wanted to say a couple of words about the exam, just very quickly. So just some general stuff. So the exam will consist of exercises. Some of them will be very similar to exercises you've seen on the problem sheets.